Hello everyone. Today I will be presenting a paper on policy contrastive imitation learning, or PCIL, a new framework for reinforcement learning based imitation learning. The motivation is simple. We want an agent to learn behaviors demonstrated by an expert, ideally by reproducing expert trajectories from a dataset. PCIL builds upon traditional imitation learning but takes a different approach toward representation learning, which we will explore throughout this talk. Classic imitation learning trains an agent to mimic an expert's behavior directly from demonstration data. The goal is for the agent to reproduce expert's behavior as closely as possible. In other words, we assume the expert already knows how to solve the task well, and we simply try to transfer that knowledge. The demonstrations usually come in the form of state action trajectories, and the agent learns patterns embedded in those trajectories. This imitation learning concept is appealing because it avoids designing task-specific objectives. PCIL extends this idea by introducing contrastive learning into the imitation process. Instead of asking, is this sample expert or not, PCIL learns a representation space that captures behavioral similarity. Through contrastive learning, an encoder is trained to separate expert behaviors from agent behaviors in an informed way. This encoder becomes a metric for evaluating how close the agent is to behaving like the expert at any moment. As the agent improves, its embeddings gradually move closer to the expert cluster in that space. This allows the agent to receive higher rewards when its behavior becomes more expert-like, leading to smoother and more stable learning. Before introducing PCIL, let's briefly review existing imitation learning approaches. First, behavior cloning, which performs supervised regression on observation action pairs. The expert observation become input data, and the corresponding actions serve as labeled ground truths. This method is simple, fast, and easy to train, but not very robust in many situations. Because the agent learns to imitate only what it has seen in the dataset, even slight deviations or unseen situations can cause failures. Second, imitation reward methods, which reward the agent based on how similar its state is to the expert state. This is particularly popular in animation and robotics, where smooth motion and physical realism matter. Since the agent doesn't need to replicate the expert's exact state action pairs in the dataset, this approach tends to generalize better than the behavior cloning. It encourages the agent to discover its own trajectory as long as the resulting behavior resembles the expert's outcome. Finally, generative adversarial imitation learning, or GAIL. This method trains a gain-style discriminator to distinguish expert samples from agent-generated samples. The agent then receives a reward based on how successfully it fools the discriminator. Because GAIL models the underlying distribution of expert demonstrations, it enables more implicit, flexible, and scalable imitation learning. PCIL proposed as an alternative to these methods, one that keeps the benefits of Gale's expressiveness while addressing its weaknesses in representation learning. PCIL begins by identifying a key limitation of Gale. Since Gale trains a binary discriminator, the representation space is forced into a binary separation. As shown in this illustration, the distance between two expert samples may appear larger than the distance between an expert and an agent. This means the trained representation space does not meaningfully reflect behavioral similarity. Because of this, the agent cannot tell how close it is to the expert, only whether it is considered expert or non-expert. So the feedback signal becomes coarse, unstable, and sometimes misleading during policy optimization. As a result, Gale struggles to provide smooth guidance, often requiring heavy hyperparameter tuning or careful reward shaping. To address this, PCIL replaces the discriminator with contrastive learning. Contrastive learning is already widely used in the vision domain because it produces semantically meaningful embeddings that transfer well to downstream tasks. PCIL borrows this strength to build a structured similarity space specifically for imitation learning. Contrastive learning method samples anchor positive, negative triplets from the dataset. Instead, in PCIL, the anchor sample is an expert transition from the dataset. The positive sample is another expert transition, and the negative sample is an agent-generated transition collected during training. The encoder is then trained so that in the learned representation space, positive samples stay close to the anchor while negatives are pushed farther away. This explicitly teaches the encoder what expert similarity looks like rather than only separating two classes with binary decision boundary. Over time, the resulting space forms a smooth manifold where behavioral closeness has geometric meaning, which means that the distance in the representation space actually reflects imitation quality. This representation becomes the foundation for defining reward and guiding imitation more effectively, because similarity in this space corresponds to meaningful behavioral alignment. To achieve this, PCIL adopts the info NCE loss. Each state action pair is passed through an encoder function pi, which maps it into an embedding vector in the representation space. This formulation is essentially the standard info NCE objective used in contrastive learning, but adapted so that triplets correspond to RL transitions instead of image patches or text tokens. The loss has a softmax form using exponential functions, encouraging high cosine similarity between the anchor and the positive, and low similarity between the anchor and negatives. Minimizing this loss clusters expert demonstration tightly while pushing agent behavior apart. And because cosine similarity depends on only on direction, It ignores magnitude and focuses on behavioral alignment. Over time, the encoder organizes expert and agent policies into a normalized unisphere structure where distances carry semantic meaning about imitation quality. This means the embedding space itself becomes a measurable indicator of behavioral similarity, which discriminator-based methods fail to provide. Once the representation space is learned, defining a reward becomes extremely simple. We randomly sample expert embeddings from the dataset and compute cosine similarity with the current agent embedding. This similarity value is used as the reward, and this is the dot product, meaning this similarity value is used as the reward, meaning the agent is explicitly encouraged to move toward expert behavior distribution in the representation space. The number of expert samples used per update in this function, reward function, is flexible and task dependent. This avoids designing handcrafted reward functions, which are often brittle and domain-specific. Instead, reward naturally emerges from the learned semantic structure of expert behavior. So the agent learns what the expert does without explicitly copying expert actions, such as behavior cloning. And for the experiment, across multiple RL imitation benchmarks, PCIL outperforms existing imitation learning baselines. In this plot, PCIL is shown in red, consistently staying above competing methods. This performance gap becomes even more pronounced in more challenging environments. The authors argue that binary classifiers, which focus only on class separation, struggle in complex tasks. In contrast, PCIL provides smooth and stable similarity signals that guide learning more effectively, leading to faster convergence, lower variance across learns, and fewer training collapses. To further support this, the authors visualize the representation space using TSNE. In DAC, which uses a binary classifier such as discriminator, expert and agent embeddings appear scattered and poorly organized. In contrast, PCIL produces a space where higher reward agent samples lie closer to expert samples, like this. This indicates that the geometry of the embedding space meaningfully reflects behavioral similarity. So PCIL isn't just performing better, it's learning a fundamentally better structure understanding of the task. To summarize, PCIL introduces a new methodology for imitation learning in reinforcement learning. It reasonably highlights weaknesses of discriminator-based approaches and emphasizes the importance of meaningful representation learning. PCIL shows strong potential on standard benchmark tasks, but its general effectiveness across broader and more complex R settings still needs further validation. Future work may explore scaling, multitask adaptation, and robustness under distribution shift. Since contrastive learning is already well established and powerful in vision domain, PCIL carries promising future applicability. So if our task depends on structure similarity or requires smooth behavioral feedback, PCIL may be worth adapting or experimenting with. Overall, PCIL encourages the field to rethink imitation, not as classification, but as representation learning. And this is end of my presentation. Thank you for listening.